In this video, we are going to introduce about our fiction design of navigation ecosystem for blind people, called eDog. Until recently, many blind and visually impaired people rely on guide dogs to navigate around obstacles. However, there are still many limitations on relying dogs for navigation. In order to provide a better navigation assistance to blind and visually impaired people, we designed and built a smartphone application which has close to human-level intelligence to perform complex routing and navigation tasks to assist our users to reach their destinations safely.
Similar navigation tools had already been designed to assist blind people to move around freely. However, they have many limitations, such as too complicated to execute when there are many obstacles, and it was hard to make reliable decisions for users.
Our ecosystem consists of three main parts, namely cameras, earphones, and backend application. The related works we built upon covers motion detection, audio interface, and outdoor navigation. Motion sensing is widely used in many application areas, such as security systems, automatic doors and lights, and video games. It also plays a vital part in robotic tasks such as autonomous path planning, obstacle avoidance, and navigation. Existing sensor technology for motion detection includes infrared, radio, ultrasonic, video camera, and gesture detector. Outstanding performance has already been achieved for autonomous navigation in clean highway traffic, but not so successful in busy inner-city environments. To address this challenge, some researchers use offline training to detect moving pedestrians but ignore other objects such as cars. Others use online training for unknown moving detection but could not recognize the objects. For our product, both object recognition and moving detection is realized to support optimal navigation planning.
Recent research had used VAR as an audio interface on devices to provide eyes-free interactions. We used a similar technology to gather audio commands from users and then send instructions back to them. Another audio GPS utilizes a non-speech and spatial audio to represent the direction at distance for users, and we also implemented this technique to interact the audio signal with our navigation system. The last technique is to handle multiple audio streams, which utilizing spatial audio and movement of the perceived location. This can improve the performance when users make simultaneous audio presentation. We used this method to optimize our system.
Outdoor navigation technology is widely used to enable robots to autonomously navigate in a crowded outdoor environment and deal with obstacle situations. Our product is just like a robotic assistant to blind people, so we apply this technology into our system to help the blind see the environment and lead them to the correct destination properly. Three main features of our software are perception, localization, and dynamic path planning. As the blind people need the real-time feedback and data transferring and processing has delay, we used retroactive precisioning data fusion technology to deal with this problem so that the feedback is non-stop. Our application used visual GPS technology to get more accurate location.
The target users of our application are visually impaired and blind people who need to move around outdoors without any others accompanying. We used the cameras to capture the real-time image and adapted highly sensitive warning and alerting system.
Our product ecosystem includes three main components, which are Eagle Eye, EarPods, and the eDog mobile app. The main input component for our application is the Eagle Eye, which has the design of normal sunglasses with cameras attached to the front and side frames. The lenses of Eagle Eye absorb and store solar energy in the batteries, which are built into the frames of the sunglasses. There is also a flashlight installed on the right rim of the sunglasses, which will turn on automatically when there's insufficient light for the cameras to operate. Besides optical detection, Eagle Eye is also equipped with acoustic sensors to measure the distance. This will enhance the performance of detection and navigation. The Eagle Eye continuously sends all capture data to the mobile app for processing. All tasks such as image analysis, object recognition, and motion detection are done by the app, not the glasses.
We used an earphone to connect the switching and feedback system with a back-end navigation system. The switch activates the app and can free users from paying attention to visual interface on the phone. We divided the function of earphones in two parts. One is the output commands from users, and the other is the output instructions from backend. For the input function, the users can send an instruction to the app through voice command. To be noticed, the application will only start executing user's command after it hears the keyword "Hey eDog." Other words will be ignored to prevent execution of false commands. For the output function, our goal is to help users make better decisions and ensure safety outdoors. The output function will give feedback in the following situations. The first one is to confirm the requirement of users. The second one is to give users error alert. Our sensitive warning and alerting system will alert users when the camera captures obstacles, and also works when users deviate from the right path. The last one is to give users alternative suggestion. Our backend system will analyze the route to the required destination, and if the route is considered too difficult for the blind, and there is an alternative destination which serves a similar purpose to their original request, eDog would suggest alternative options to the user.
We installed our software system eDog app on a mobile phone, which is responsible for all the data processing and analyzing, so our application is portable. We divided our background system into 4 functions. The first function is data transferring. The mobile software takes 2 types of data, which are audio data and real-time image video. They all come through Bluetooth. The second function is navigation. Navigation is the most important function in the system. It has 2 modes, normal mode and obstacle mode. The functions of normal mode are routing and localization. First, routing function is allocating the destination location in the embedded online map and getting a proper route. Localization function uses artificial GPS technology to get the accurate current location, and retroactive precisioning data fusion technology to offer a non-stop navigation when the DGPS technology fails or the data processing and transferring delay is unreasonable. Obstacle mode works when the system detects an obstacle or traffic signals. In this mode, the system calculates another path to lead the user bypass the obstacle. If the road is closed, the system reroutes to the destination. When the system recognizes a traffic signal, it sends the message to instruct the user to act according to the traffic rules. Third function is detection. Detection function receives real-time image, video, data string, and sonic information from the Eagle Eye. According to the received information, the system can instantly segment any static or dynamic obstacle or traffic signals and recognize the objects via online self-supervised learning. The final function is searching. Searching function searches the places that are similar to the user's destination and recommends some closer places to the user when user indicates a location and the route is complicated. Here are some scenarios of our system. First, our eDog system can go to the set destination properly. Next, our system can help users go across the road. Third, our system can change route when user instructed. Fourth, our system can help users avoid obstacles. Last, our system can recommend similar destination when the routes of users' original desired destination were too complicated to go.
We conduct an initial trial of eDog system on 2 blind people and 2 visually impaired people. We use it to evaluate the usability of our product by asking them to complete the scenario tasks mentioned earlier. To evaluate the accessibility and credibility of the system, we encourage participants to express their feelings to the developers during the trial. At the end of the trial, all participants were asked to take part in feedback sessions. So that's a brief introduction about our fiction design. For more information, please refer to our report, and thanks for watching.